Hi guys, in this chapter we're going to be looking at all of the different functional groups. So I thought we'd start off by looking at what they are so we can familiarize ourselves with them. So for now we don't have to worry about memorizing any of these right now, but I would recommend just spending a minute going through these. So we'll do that together so we can understand these a little better. And then throughout this chapter we're going to have a lesson on each of these different functional groups and learn more about their naming and their properties. So the first one is an alkane. So this is kind of like the simplest one. It's just when you have carbons and hydrogens and it's all single bonds. Okay, and then an alkene is still referring to having carbon and hydrogen, but here we now have a double bond. So it's a double bond between two carbon atoms. And then we have an alkyne as well, which is another type of hydrocarbon. So it's just carbons and hydrogens, and here you're going to see at least one triple bond between two carbon atoms. Okay, so another type of hydrocarbon is a benzene ring, and this is a specific group that we have when we see that 6 carbons are bound in a ring, but it's not just any regular ring. We also see that there's these bonds here. And for a benzene ring specifically, these have resonance, so this double bond can push down here, this double bond can push down here, this double bond can push down there. So it's actually more like each of the carbon-carbon bonds are kind of halfway between a single and a double bond. So that's a unique scenario, and we'll learn more about naming and properties of the benzene ring because it is quite different. Okay, in the next row we see that we have an amine. So that is when we have a nitrogen in our chain. So anytime we see this, it's just a short form for the rest of the chain. So maybe there's 4 other carbons and we have the nitrogen that's a part of that chain. So that's an amine. So we'll see a nitrogen. That's kind of the way that you know that it's an amine, and we don't see any double bonds here. So that's how we know it's different from the amide, which we'll see later on, which involves a double bond between carbon and oxygen. And we call the double bond between carbon and oxygen a carbonyl group. And then right away, the first bond from that carbon is going to be bound to a nitrogen, and in that case we have an amide. So then an alcohol is just when we have an OH, so anywhere in the molecule, if we have an oxygen bound to a hydrogen, that's an alcohol. An ether is when we have a carbon chain, so it's showing 2 carbons on either side of an oxygen. So anytime carbons are surrounding a single oxygen atom, we call that an ether. An alkyl halide, so the alkyl part is referring to whatever carbon chain you have. So, it could be 1 carbon, 2 carbons, so on, it doesn't matter. And the halide part is referring to a halogen. So these 4 halogens, fluorine, chlorine, iodine, and bromine, we'll look at how to name those when they are part of a carbon chain, and we call those alkyl halides, or you might also see them being called haloalkanes. And again, the halo or halide part is because it's from a halogen, which is the second last group of the periodic table. Okay, so now the bottom row all involves the carbonyl group, so carbons bound to oxygens in a double bond. If we just have an aldehyde, that means that we have whatever carbon chain, and then this group is on the last possible carbon. So if you see a carbonyl group at the very end of the carbon chain, then we call that an aldehyde. So then we see that on this side it's just bound to a hydrogen. Whereas if the carbonyl group is in the middle of the chain somewhere, so not on one of the ends, so what we see here, so here it's a chain continues, so it could be a bunch of carbon bonds, and here it also continues, and then we see a carbonyl somewhere in the middle, we call that, instead of an aldehyde, we call that a ketone. Okay? Next we have an ester, which is when we have a double bond between carbon and oxygen, so again that carbonyl group, but that carbon is also going to be bound to an oxygen atom, so that's specifically called an ester. And then this one's pretty similar, but this is when that occurs on the end of the chain, and the oxygen, instead of being bound to a carbon like it is here where that chain can continue, the oxygen is bound to a hydrogen, and we call this one a carboxylic acid. So a way to remember that is that this one is a little bit acidic because it has this proton that is connected to this oxygen, and then this group is polar, which we'll talk about later. So there are ways to help us remember, but for now we're just trying to get ourselves familiar with them and know what these different types of functional groups look like. But again, we're going to look into these in a lot more detail, and we talked about the amide one being the one with a carbonyl group bound to a nitrogen. So let's just talk a little bit more about what we can learn just from knowing a functional group. So a functional group, so for example, knowing that an alcohol is present or knowing that there's a double bond present, an alkene. So this can tell us information about solubility. So certain functional groups are going to be more polar than others. So one example is the carboxylic acid. It's very polar. It has these two oxygens very close to each other. It has the carbonyl group and the electronegative oxygen, so it's going to be quite polar. Whereas if we compare that to, let's say, the alkane, it's just a very large carbon chain, and there is no polarity there, and so it's non-polar molecule. So just knowing functional groups can help us get an idea of if something is soluble or something is polar. So if something is polar, it's actually going to be dissolved or going to be able to dissolve in polar solvents. Whereas if something is nonpolar, then it likes to be around things that are like it. So it likes to dissolve in other nonpolar solvents. So just for understanding, a common example is water and oil. So oil is just long carbon chains pretty much, so they are very nonpolar. Whereas water, we know that water looks like this and has hydrogen bonds, which make it very polar. And when we say something is polar, it's because there's a difference in electronegativity that does not get canceled out. So if something has a dipole moment, so in this case, let's just look at the electronegativity first. The hydrogens are not very electronegative, so we draw a delta plus for the hydrogens, whereas the oxygen is electronegative, so we draw a delta minus there. Okay? And we know that the oxygen is electronegative because if you look at a periodic table, electronegativity increases as you go up and to the right. So fluorine, just for a reference point, is the most electronegative atom. So that's how we know oxygen is also quite electronegative, because it's in the top right of the periodic table. And that rule doesn't apply for noble gases since they're very stable. But other than the noble gases, as you go up and to the right, you increase in electronegativity. And nitrogen is another very electronegative element. So fluorine, oxygen, and nitrogen are your top 3 electronegative elements. So that means that it's going to be pulling electrons towards it, and we can draw dipoles along each bond that point towards where the electrons want to go, and then we can draw a net dipole here. So because both arrows are pointing like this, if we wanted to draw one overall arrow, it would go like this. You guys wouldn't have to do that. I'm just trying to show you that because this molecule, we can draw a net dipole, it has a dipole moment, that's how we know that it's polar. And then if we were asked what type of solvent would a polar substance want to dissolve in, a polar one or non-polar, then you just want to remember like dissolves like. And we'll review this again as we go through the different functional groups and talk about their polarity and what they like to dissolve in. So it'll get repeated, so it'll make more sense. But pretty much like dissolves like is just something that helps us remember that polar substances like to dissolve with other polar substances, and like we said, non-polar substances dissolve in non-polar solvents. Okay. The other thing that we can learn about functional groups is based on the functional groups and based on the overall molecule, we can make educated guesses about their melting points and boiling points. So we can know, if we compare two functional groups, we can know if one would have a higher or lower melting or boiling point. So the trend is pretty similar to polarity for melting and boiling point. Let's say we compare our alkane and carboxylic acid again. So we said that carboxylic acid is very polar. It has this electronegative oxygen and there as well, and it's also able to hydrogen bond, which we'll talk a little bit more about later, but pretty much it's able to hydrogen bond because we see that it not only has this electronegative element, but it's also bound to it has a hydrogen bound to an electronegative element. So this makes it able to have a lot of hydrogen bonding. And so because it's able to have those strong interactions and is polar, it makes it harder for it to break apart. So that means if I was trying to put in energy to break this molecule apart, it's going to take more energy to break it apart because its bonds are stronger and it has these electronegative elements that make the bonds polar and make the bonds stronger. And so the boiling point of carboxylic acid would be quite high. I would need to put quite a bit of energy to break it apart. Whereas for an alkane, we don't see any of those electronegative elements. We mentioned that it's nonpolar, so it's a lot easier to break apart, and so the boiling point would be lower. I don't have to put in as much energy to break those bonds. And again, we'll talk more about this. It's just kind of introducing how we can know melting and boiling points are higher or lower for different functional groups in general. And then also, functional groups can determine which molecules can readily react with other molecules. And we'll look at some reactions in this chapter, but mostly reactions we'll be focusing on in the next chapter. So 3 main components of functional groups. This, again, you don't need to memorize this. It's just helping us kind of wrap our head around all the different functional groups. So it says there are many different functional groups, but essentially they consist of 3 main components. So there are ones with carbon-carbon multiple bonds. So we said that an alkene was the one with a carbon-carbon double bond, and an alkyne was the one with carbon-carbon triple bonds. So again, we can see those right here, the double bond and the triple bond between carbon atoms. Then there are other functional groups with a single bond between a carbon atom and a more electronegative atom. So we see functional groups with a carbon bound to an oxygen in a single bond, a carbon bound to a nitrogen in a single bond, and a carbon bound to something like a chlorine or a halogen in a single bond. So if we look at those, this one is an example of carbon bound to nitrogen. Here in alcohol, we have a carbon bound to an oxygen. An ether is also a carbon bound to an oxygen. Alkyl halide is a carbon bound to an electronegative halogen atom. And then finally, we have a bunch of different functional groups where a carbon atom is double bonded to an oxygen atom. And we see those in the last row where there's all these carbonyl groups, which is referring to the carbon double bonded to the oxygen atom, and all of these have that. And they also, some of them have carbon single bonded to oxygen or nitrogen as well. So now that we have a general idea of the different functional groups, we'll be soon going into all of these in detail, starting with the alkanes.